Hello everyone. Let's study the history of the Earth. The origin of the universe. The universe began about 14.4 billion years ago. The Big Bang theory states that in the beginning the universe was all in one place. All of its matter and energy were squished into an infinitely small point, a singularity. Then it exploded. A tremendous amount of material blown out by the explosion eventually formed the stars and galaxies. After about 10 billion years, our solar system began to form. The birth of the solar system. We know how the Earth and solar system are today, and this allows us to work backwards and determine how the Earth and solar system were formed. Plus, we can go out into the universe and look for clues on how stars and planets are currently being formed. The nebular hypothesis. In cosmogony, the nebular hypothesis is the currently accepted argument about how a solar system can form. Other solar systems. We have now discovered over 200 planets orbiting other stars. The processes that created our solar system have also created an uncountable number of other solar systems. The nebular hypothesis. A large gas cloud nebula begins to condense. Most of the mass is in the center. There is turbulence in the outer parts. The nebular hypothesis. The turbulent eddies collect matter measuring meters across. Small chunks grow and collide, eventually becoming large aggregates of gas and solid chunks. The nebular hypothesis. Pictures from the Hubble Space Telescope show newborn stars emerging from dense, compact packets of interstellar gas called evaporating gaseous globules. Gravitational attraction causes the mass of gas and dust to slowly contract and begins to rotate. The dust and matter slowly falls towards the center. The protostar. As a result of contraction and rotation, a flat rapidly rotating disk forms with the matter concentrated at the center that will become the protosun. False color image of protostar. The multicolored area shows a dust disk surrounding a newborn star. The red-orange area at the center represents the brightest region, which contains the young star. It is surrounded by the cooler, dusty disk, which appears as yellow, green, and blue. The diameter of the disk is about 20 times larger than our entire solar system. The Sun. After sufficient mass and density was achieved in the Sun, the temperature rose to 1 million degrees Celsius, resulting in thermonuclear fusion. One hydrogen atom plus one hydrogen atom is equal to one helium atom plus energy. The birth of the solar system. The enveloping disk of gas and dust form grains that collide and clump together into small chunks or planetesimals. The protoplanets. Gravitational forces allow the inner planets to accrue and compact solid matter, including light and heavy atoms. Solar radiation blew gases, primarily hydrogen and helium, away from inner planets. These gases were collected and condensed into gas giants Jupiter, Saturn, Uranus, and Neptune. Beyond Neptune, ice and frozen gases form Pluto, Sedna, and the Kuiper Belt objects. Leftover debris form comets and asteroids. The birth of the solar system. The terrestrial planets build up by multiple collisions and accretion of planetesimals by gravitational attraction. Giant outer planets grew by gas accretion. Size of the planets. At the left side, we can see Mercury, Venus, Earth, and Mars. They are called the inner planets. Mercury has 2,440 kilometer radius. Venus has 6,052 kilometer radius. Earth 6,371 kilometer radius, and Mars 3,390 kilometer radius. At the center, we can see the outer planets Jupiter, Saturn, Uranus, and Neptune. Jupiter has 69,911 kilometer radius. Saturn has 58,232 kilometer radius, while Uranus 25,362 kilometer radius and Neptune 24,622 kilometer radius. At the right side, we can see Pluto. It is the dwarf planet which has 736 miles radius. The age of the Earth. Earth is approximately 4,570,000,000 years old. Meteorites give us access to debris left over from the formation of the solar system. We can date meteorites using radioactive isotopes and their decay products. Geologic time. At about 4,570 million years ago, the Sun and accretionary disk formed. At 4,000 million years ago, it is the end of heavy bombardment. The earliest evidence for liquid water is found at about 3,800 million years ago. The earliest evidence for life is found at about 3,500 million years ago. At about 2,500 million years ago, the major phase of continent formation was completed. At about 565 million years ago, there is a worldwide distribution of multicellular organisms. There is a series of mass extensions before the appearance of our species as about 0.12 million years ago. Bombardment from space. For the first half-billion years of its existence, the surface of the Earth was repeatedly pulverized by asteroids and comets of all sizes. One of these collisions formed the Moon. Formation of the Moon. The giant impact hypothesis predicts that around 50 million years after the initial creation of Earth, a planet about the size of Mars collided with Earth. This idea was first proposed about 30 years ago, but it took calculations by modern high-speed computers to prove the feasibility. This collision had to be very spectacular. A considerable amount of material was blown off into space, but most fell back into the Earth. Formation of the Moon. Part of the material from the collision remained in orbit around the Earth. By the process of collision and accretion, this orbiting material coalesced into the Moon. The early Moon orbited very close to the Earth. The early Earth heats up. There are three major factors that caused heating and melting in the early Earth's interior. First, collisions, the transfer of kinetic energy into heat. Second, compression. Third, radioactivity of elements, example, uranium, potassium, or thorium. The core. About 100 million years after initial accretion, temperatures at depths of 400 to 800 km below the Earth's surface reached the melting point of iron. In a process called global chemical differential, the heavier elements, including the melted iron, began to sink down into the core of the Earth, while the lighter elements, such as oxygen and silica, floated up towards the surface. Global chemical differentiation. This global chemical differential was completed by about 4.3 billion years ago, and the Earth had developed an inner and outer core, a mantle, and crust. The chemical composition of Earth. Each of the major layers has a distinctive chemical composition, with the crust being quite different from the Earth as a whole. The whole Earth consists of 93% iron, oxygen, silicon, and magnesium. The rest consists of other elements. The crust consists of 82% of silicon, oxygen, and aluminum. The rest is composed of iron, magnesium, calcium, potassium, sodium, and other trace elements. The chemical composition of Earth, lithosphere, is a strong rocky outer shell of the solid Earth, including all the crust and the upper part of the mantle to a depth of approximately 100 km. It forms the plates. A stenosphere is a weak ductile layer of the mantle beneath the lithosphere. It forms to accommodate the motions of the overlying plates. Deep mantle, a mantle beneath the asthenosphere, approximately 400 to 2,100 km in depth. Outer core is a liquid shell composed of mostly iron. The inner core is the innermost sphere composed primarily of solid iron. Continents is formed from solidified magma that floated up from the mantle. Oceans and the atmosphere. Fluid and gases, outer layers, believed to have been created by outgassing of gases and fluids from volcanic eruptions, in a process called volatile transfer. The evolving atmosphere. Right after its creation, the Earth is thought to have had a thin atmosphere composed primarily of helium and hydrogen gases. The Earth's gravity could not hold these light gases, and they easily escaped into outer space. Today, hydrogen and helium are very rare in our atmosphere. For the next several hundred millions of years, volcanic outgassing began to create a thicker atmosphere, composed of a wide variety of gases. The gases that were released were probably similar to those created by modern volcanic eruptions. Evolving atmosphere. This would include water vapor, sulfur dioxide, hydrogen sulfide, carbon dioxide, carbon monoxide, ammonia, and methane. Note that oxygen gas is not created by volcanic eruptions. Creating the oceans. It is hypothesized that water vapor escaping from the interior of the Earth via countless volcanic eruptions created the oceans. This took hundreds of millions of years. Astronomers also hypothesized that comets impacting the Earth were a major source of water that contributed to the creation of the oceans. Remember that comets are best described as dirty ice balls. A billion-year-old Earth. By 3.5 billion years ago, when the Earth was a billion years old, it had a thick atmosphere composed of carbon dioxide, methane, water vapor, and other volcanic gases. By human standards, this early atmosphere was very poisonous. It contained almost no oxygen. Remember, today our atmosphere is 21% oxygen. By 3.5 billion years ago, the Earth also had extensive oceans and seas of salt water, which contained many dissolved elements, such as iron. But most important, by 3.5 billion years ago, there was life on Earth. The continents. By 2.5 billion years ago, the continents had been formed. The density of the continental crust which is 2.8 gram per cubic centimeter, is lighter than the crust found on ocean bottoms, which is 3.2 gram per cubic centimeter, so the continents rise above the ocean floor. A question that remains unanswered is, when did plate tectonics start? Thank you.